Hello friends and welcome to CEC live lectures. In the ongoing lecture series on extraction of natural products, in the last two lectures we started with the microwave assisted extraction, and in those lectures we discuss about what are microwaves, and then I gave you a brief historical overview that how the use of microwaves evolved over the period of time from its use in radar or telecommunications to heating and cooking in daily household activities, and then in the scientific arena for extraction or enhancing the reaction speeds as well as their yield. Then we move on to the instrumentation aspect of microwave, wherein we discuss certain general points that one has to keep in mind while designing a microwave assisted reactor or extractor. After that, we discuss the components that are involved, such as magnetron, which is the heart of the microwave. What are the different types of magnetron over the period of time, like vacuum tube assisted, then single anode, split anode, and cavity anode, which is now the most commonly used type of magnetron. We also discuss that how magnetron works and produces microwaves. After that, we discuss different types of cavities of the microwave extractors or reactors, and in that we discuss monomodal or focused mode microwave mode cavities, then multimodal cavities and continuous flow cavities. We also discuss about their advantages and disadvantages. This was followed by the different types of extraction vessels that are used in microwave reactors, and the two major vessels were open system and the closed system. And we discussed that by and large monomodal cavities utilize the open system vessels, whereas the multimodal, they require the closed system. But if we look into the current scenario, then for open as well as for the closed vessel system, both monomodal and multimodal cavities are available in the market. Again, we also discuss about the various advantages and disadvantages of both the extraction vessels. So friends, in continuation with the lecture on microwave assisted extraction, today we will discuss with the other components that are involved in a microwave reactor or extractor. So the next component is the temperature sensors, and there are different types of temperature sensors that are being used in microwave extractors, and these are thermocouple, optical pyrometers, thermal cameras and optical fibers. Amongst these four commonly used temperature sensors, optical pyrometers and thermal cameras, these are the non-contact method, as they are not in contact with the material which is under microwave irradiation. So coming on to the thermocouple sensors, now it has been found that these thermocouple sensors are nothing but these are a sort of metallic rod, or they have a metallic sheath which cover the sensors, and these sensors are fitted in a microwave extractor or the reactor, and on the outer side they are attached to a thermostat which help in regulating the temperatures. Now this metallic nature or the metallic nature of the sheath that covers the sensor is normally not recommended in the electromagnetic environment, because it has been found that this metallic sheath or the metallic nature of these sensors, it produces certain type of disturbances in the electromagnetic radiation field or the area, and this disturbance is largely related to its improper distribution. So in simple words, if I talk about, we can say that the metallic nature of these sensors, they help, or I will say they will disturb the homogeneous distribution of microwaves, and therefore these are generally not recommended. Furthermore, it has been found that there are certain needle shaped thermocouple sensors, and when they were used in microwave extractors or reactors, it was found that these needle shaped sensors, they favor the concentration of electromagnetic radiations or microwaves to their tips, and this kind of behavior causes the localized overheating of the of the material that is subjected to the microwave irradiation. And these are the two prominent reasons why thermocouple sensors are not recommended nowadays for the microwave reactors. Second type of sensor is the optical pyrometers. Now, you can always remember these optical pyrometers by a common name of the thermal guns. And I am sure everybody must have seen those thermal guns during the COVID times when the body temperatures were measured and the guard, in whatever building you enter, the guard was standing with those thermal guns, and it point that gun either to your forehead or onto your back of the hand to measure the temperature. And you must have observed that they don't touch the skin of the person whose temperature is being recorded, and therefore these optical pyrometers are nothing but these are the non-contact thermal sensors. But the major problem with these optical pyrometers is that they only record the surface temperature, because if you remember the previous lecture where I discussed the difference between the microwave assisted heating vis-a-vis conventional heating, we discussed that since microwaves are absorbed by the particles, they start heating that particle from its central core, and from the central core that heat is radiated towards the surface. Whereas in case of conventional heating, the heating takes place with the conduction process, wherein the heat is applied from the outside and gradually that heat transfers to the central core of that particular particle. So since microwaves are absorbed by the particle and they first cause heating of the central core, whereas the optical pyrometers, they only record the surface temperature, and sometimes we don't get the exact rise in temperature conditions when the subject or the material is exposed to microwave irradiation. This is one of their disorder. Further, many times it has been observed that whenever a particular reaction is being carried out in a microwave, or extraction is being carried out in a microwave, it causes evaporation of the solvent, and sometimes it makes the environment smoky inside. And under the smoky conditions, the readings that are obtained by optical pyrometers are not so reliable, and therefore they have a very limited utilization in the microwave extractions or the microwave reactors. Next temperature sensor is the thermal cameras, and generally by and large, if we see, these thermal cameras are meant to observe the variations in the temperature in the larger areas, and therefore they have main use in the industrial arena. Further, these thermal cameras are largely used to monitor the excess increase in the temperature on the surface. Therefore, we can say that thermal cameras are largely meant for the safety, to consider the safety aspects of the reactors. Again, mind you, these thermal cameras are the non-contact method, and therefore they will provide you only the surface increase in the temperature, and therefore again their utility is quite limited in case of microwave extractors, or it is only limited to the industrial use, with a very with these demerits, because they only measure the surface temperature and they just provide you whether the temperature has been exceeded beyond the prescribed limit. Again, the major aspect in this is when they have to tell you that yes, now the conditions are such that it has exceeded the required temperature, whatever input has to be given to the controller should be foolproof. There should not be any variation in the feed to the controller which controls the sensor. So if there is any kind of variation in the actual conditions and the feed that is given to the controller, again these thermal cameras have certain limitations in that area also. Last is the optical fibers, and optical fibers are nothing but these are the contact type of temperature sensors, because these fibers are in direct contact with the material which is exposed to the microwave irradiation. All other temperature sensors like thermal cameras or optical pyrometers, they were meant to observe the temperature of the load, whereas optical fibers, they help you in determining the temperature in the load, that is in the central core of the load that is subjected to the microwave irradiation, and this is one of their major advantage. Second, in carrying out the temperature measurements with optical fibers, many a times it has been observed that certain reactions, they produce certain corrosive environment inside the microwave. Or whenever you are extracting a particular herbal drug material with a solvent, it may provide certain harsh environment inside the extraction cavities. And these optical fibers, since they are the contact type of thermal sensors, they have to withstand those harsh conditions, and therefore sometimes they are coated with polytetrafluoroethylene, that is PTFE, in order to protect these fibers from those harsh conditions or the environments. Another major advantage of optical fibers is that they have a very wide temperature range, that is, it ranges from the sub-freezing temperatures to 1500 degrees Celsius. But this wide range also has certain disadvantages, because it has been found that single optical fiber usually is not able to cover the whole temperature range. Therefore, you have to install different types of optical fibers covering the entire range, and each optical fiber has to be connected to a different controller. So this basically slightly increased the input cost of the microwave reactor, but in return it will provide you the overall or the broad monitoring range of the temperatures. Then from time to time, optical fibers, they are exposed to the temperature conditions which surpasses their maximum limit, because as I told you, different optical fibers have to be installed to monitor a particular range of a temperature. And therefore those fibers, say for example you have loaded the optical fibers ranging from 0 degrees to 100 degrees, then 100 degrees to 300 degrees, and 300 to 500 degrees Celsius, and you are carrying out a reaction say at 250 degrees Celsius. Now those optical fibers which have a range of say 0 to 100 degrees Celsius, now they are exposed to temperature conditions which are beyond their maximum usage limit. Therefore, under such conditions, one has to regularly replace those optical fibers, because whenever optical fiber is exposed to a particular temperature limit which is beyond its maximum limit, the sensitivity of those fibers tend to decrease. So they must be regularly removed and replaced by the fresh fibers. Now we move on to the pressure sensors. Now, there are different types of pressure sensors that are being utilized in microwave extractors or reactors. These are namely piezoelectric sensors, membrane sensors, and the load cells, which are commonly used. Now, apart from these commonly used sensors, there are specific sensors that have been designed to critically monitor the change in pressure. And such sensors largely depend upon the change in the optical properties of that particular sensor. And one such sensor is the glass ring sensor. And whenever the glass ring is exposed to the changing pressure, it has been found that there is a change in the color of the transmitted light. And this change in the color of the transmitted light is largely dependent upon the change in the pressure. So if the pressure exceeds the prescribed limits or the limits to which that sensor is sensitive, then obviously it will change its color to a specific color, by which you can know that the pressure now has been exceeded to the prescribed limits. Obviously nowadays modern equipments come with the automated system where these sensors are connected with certain other mechanism which causes complete stoppage of the instrument, but it also alerts the manual or the user who is operating that instrument. Then last but not the least is the fiber optics, and these fiber optics again are very sensitive type of sensors, and the measurement of the change in the pressure in case of fiber optics is largely dependent upon the change in the cavity length of those fibers. And cavity length is nothing but it's a small part or the area of the optical fiber that is surrounded by semi-transparent mirrors. So whenever there is a change in the pressure conditions, the length of the cavity or the area of the cavity changes, and that is indicated by certain signals that are mounted with the extractor or the microwave reactors. So these were some of the important components that are utilized in manufacturing a microwave extractor or the reactor. Now we move on to the another aspect of microwave assisted extraction, that is, what are the factors that can affect the extraction efficiency of microwave extractor. These are type of solvent. Now type of solvent, irrespective of what kind of technique you are using for extracting the plant material, is one of the most critical factors, because if you remember, I discussed in my first two lectures wherein we discuss about the basics and fundamentals of extraction process. It is the solvent that is responsible for the solubility of the compounds which one wants to extract out of the plant matrix. So if your solvent does not have the proper solubility profile, then whatever technique you may use, the yield of the extraction will be very low. So type of the solvent, it's not only the solubility but the selectivity of the solvent is important. Second factor is the solvent to feed ratio, or you can also say solvent to the drug ratio. If we increase the solvent in comparison to the drug amount, obviously initially there will be an increase in the yield, but sometimes such increase in the solvent volumes will make whole extraction process uneconomical because of the increased cost of the solvent that is involved. Further, since the volume of the solvent has been increased, a large amount of energy will be required to heat up that volume of the solvent. It will also increase the overall extraction time, and more energy will be required to concentrate that solvent. Then temperature and pressure. We know that these two factors are also important in increasing the overall extraction efficiency, and as you increase the temperature, the viscosity of the solvent decreases. Viscosity of the solvent decreases, it increases its penetration ability into the plant matrix and increase the solubility. Further, it has also been found that temperature also sometimes increase the intermolecular collisions in the solvent, which also causes increase in the solubility aspect. Further, pressure helps in increasing the penetration of the solvent into the plant matrix. Vis-a-vis, it also helps in keeping the solvent in liquid form even when it is boiled or heated above its boiling point. Next factor is power. Higher the power, better will be the extraction, but one has to optimize power along with the extraction time. Obviously, I will be discussing all these factors with suitable examples in detail ahead. Then extraction time, and yes, time will higher the time for the extraction, better will be the extraction, but again optimized time duration should be there, because in many cases it has been found that if you increase the time limit beyond a specified limit, then there is no considerable or significant increase in the overall yield. But yes, if you further increase the time of extraction beyond that point, that increase in time will obviously have a negative impact on the overall cost involved in that extraction process. Next factor is the matrix nature, and when we talk about the nature of the matrix, particle size is one factor, and second is the presence of moisture. As I discussed in my previous two lectures, that water is a highly polar solvent, and whenever it is exposed to microwave radiations, because of its polar nature, and it causes the dipole rotation of the molecules. Now this dipole rotation helps in absorbing the microwaves and cause the heating. On the other hand, the water has a very low dissipating factor, therefore it will cause superheating of the particles, but it will not dissipate heat to the surrounding, thereby not heating up the surroundings. So only localized heating will be there. So moisture is important, but moisture amount has to be optimized. And last but not least, the factor is stirring. Now we will discuss each and every factor. So coming on to the solvent. So as I discussed, solubility is an important aspect of the solvent selection. Irrespective of the technique you are following, whether it is a modern technique or it's a conventional technique, whatever type of constituent you want to extract, the solvent should have high solubility for those type of constituents. And not only solubility, but selectivity of the solvent should be there, and your solvent should focus upon only the targeted compounds. Though practically such kind of selectivity is very difficult in case of natural products, because we know that natural products contain different types of compounds. When I say different types, it means they have wide range of chemical nature, ranging from non-polar to medium polar to highly polar constituent. And when you select a particular solvent, as in the case of natural products, most commonly used solvents are methanol, ethanol or hydroalcoholic mixtures. These solvents have a wide solubility range, and that is why I said practically selectivity is very difficult to attain in case of natural products. Further, whatever solvent do we use, it should not interact with the plant matrix, neither it should change the chemical nature of the chemical constituent you want to extract out. When I say interaction with the plant matrix, it should not have any detrimental effects on the matrix particles, nor it should have a detrimental or degradative effects on the chemical nature of the constituents. Next factor is important because we are dealing with the microwave assisted extraction. So the prime character of the solvent that has to be utilized for microwave assisted extraction is that the solvent should able to absorb the microwaves, and those solvents which have high dielectric constant, they are able to absorb the microwaves, or in other words we can say highly polar solvents are able to absorb the microwaves, and therefore they can cause heating. It's not only the solvent should have dielectric constant. In addition to dielectric constant, solvent should also have high dielectric loss. Now I will again take you back to my previous lecture wherein we discussed the dissipating factor, that is tan delta, which was the ratio of epsilon double prime to epsilon single prime. Epsilon double prime was nothing but the dielectric loss value. So higher the dielectric loss value, higher will be the dissipating factor, and we know higher the dissipating factor, better will be the heating of the surroundings. Particle will get heated by absorbing the microwaves, but it has to dissipate that heat to the surroundings in order to get uniform and rapid heating of the mixture. So whatever solvent you select for microwave assisted extraction, it should have high dielectric constant, vis-a-vis it should have more higher dielectric loss. You can also use solvents with low dielectric constant if you want to extract volatile constituent or thermosensitive constituents. Now these solvents which have low dielectric constant, since they are not able to absorb the microwaves, these solvents are known as microwave transparent solvents, and one such example is hexane. How the use of these microwave transparent solvents helps in extraction, that I will discuss ahead in by taking an example wherein we extracted the volatile oils using the hexane. Now when you are selecting a particular solvent, you can use a single solvent with good microwave absorbing property, which we have already discussed. Now I have taken an example wherein we extracted oleanolic acid and urusolic acid from the fruits of Canomelis sinensis, and different solvents were used like methanol, absolute ethanol, 95% ethanol and chloroform, and the results showed that methanol gave the maximum yield. Now methanol is a solvent which is not considered suitable for extracting out oleanolic acid or ursolic acid because of the chemical nature of these chemical constituents. So selectivity is poor, or the solubility is poor, but the presence of microwaves and the ability of methanol to absorb the microwaves and having high dissipating factor, it changes the overall scenario, and better yield was obtained in case of oleanolic acid and ursolic acid in comparison to the other solvents that were used. You can also prepare a mixture of solvent which contains both high and low dielectric losses, because the solvent with high dielectric loss will cause heat to dissipate, causing the surroundings to heat up very rapidly, and the solvent with low dielectric loss will cause the core of the particle to heat up, thereby causing rupturing of the cells and release of the constituent into the solvent, thereby increasing the overall extraction efficiency. So for example, I have taken a mixture of methanol and water into 85:15 ratio, and it has been found to a very good solvent for extracting out genin from the Gymnema sylvestris. Again, methanol is a solvent having high dielectric loss, where water is having a low dielectric loss. Third scenario is wherein you can use a solvent with high dielectric loss and microwave absorption could be immersed in the solvent with low dielectric losses. This was the example which I was taking, wherein hexane is having low dielectric loss and is a microwave transparent solvent. And if you want to extract volatile oil, obviously volatile oil is normally extracted from the fresh drug which contain high amount of moisture. This moisture will help in rupturing of the cell because it will cause superheating effect into the particles, and since hexane is microwave transparent, it will remain cool. So whatever volatile constituent are released by rupturing of the cells, they will enter into a cool solvent, and this is how you can extract out the volatile constituent by using microwave transparent solvents. So friends, in the next lecture we will discuss about the other parameters that can affect the extraction efficiency of microwave assisted extraction. Thank you.